Dr. Martin Søndergaard is a highly experienced professor at the Institute of Ecoscience in Aarhus University, Denmark. He has been specializing in freshwater ecology and applied research since 1985, contributing with more than 400 publications. His research has been mainly focused on biogeochemical nutrient dynamics, nutrient cycling, biological structure, and trophic interactions. He has done significant work on nutrient dynamics in lakes, studying the impact of phosphorus, the recovery and restoration of lakes after nutrient loading reduction, and the implementation of the European Water Framework in Denmark. He has also conducted studies on the effects of climate change on the thermal structure of lakes and its impacts on nutrient dynamics and biota. He's also an associate editor of Inland Waters, one of the journals of our society. Let's welcome Professor Martin Søndergaard and thanks him for sharing his expertise and time with us in this seminar entitled Internal Nutrient Dynamics in Lakes. Thanks, Martin.
Thank you, Maria, for this introduction. And I will see if I can start sharing. Maybe this one. And then we'll take this one here. Can you see it now?
Yeah.
And you can see my pointer here as well?
Yes.
That's fine. Then let's start. I'm not quite sure how long time this will last, but I would like to have some time in the end also to have questions from you, because that's very nice to have a discussion. It's a seminar, not just a presentation. So therefore that would be nice. But I'll use maybe half an hour, maybe a bit more on this topic on the internal nutrient dynamics in lakes. And just a moment. And when I talk about nutrients, it's actually mainly about nitrogen and phosphorus, and it's also mainly based on the findings we have from the Danish and mainly lowland lakes in Denmark. But I guess in most of the findings we have here can be translated to many parts of the world, because these shallow lakes are quite common all over the world. So I think many of the things we know from these lakes can also be used in your countries. First of all, I would like to show this one. This is just to address how important that nutrients, and especially phosphorus, are for the conditions in the lakes. It's a little bit complex figure, but it's just to show that along a gradient in phosphorus, there's a lot of things going on in the lakes. The chlorophyll increase, secretive decrease, the macrophytes decrease, the change in the fish composition. You get more species that depend on eating zooplankton and so on. And the ratio between the zooplankton and phytoplankton decreases. So that means that the capacity for the zooplankton to graze down the phytoplankton will be very low. So they become very eutrophic and dominated by phytoplankton. So this is just to set the frame that nutrients are important in our lakes and determine how the states actually are. You can also ask whether this is nitrogen or phosphorus, what is most important. And to start this, I will show this from, it was an old work from Canada, from Schindler, back in the 70s, I guess. And he had this experiment where he took a whole lake and then split it into two, and one was added phosphorus and the other was not. And then you could see this huge impact on the chlorophyll in the lake. So that has been very influential on the way that we actually manage our lakes, because we mainly try to focus on reducing the phosphorus concentrations, because that way we can also control the phytoplankton and the structure of the lake. But it may be a bit more complex than that, because if you try to look, in this case, it's a lot of Danish lakes, almost 500 lakes, where you see the total phosphorus and its total nitrogen in the water as an average for the whole year. And if you use the ratio, this is NP22 and NP9, this is where you usually say it's limited by nitrogen or phosphorus. then you find there's certainly a lot of lakes that are potentially limited by phosphorus, but there are also quite a few that are potentially limited by nitrogen. And in between, there's a lot of lakes that may be both actually. So sometimes maybe by phosphorus and other times maybe by nitrogen. So this is just to point out that it's maybe not so simple as we expect or hope just to reduce the phosphorus. There's another one here. It's also a bit complicated, but it shows again a lot of Danish lakes. It's divided into shallow lakes that are mixed all the time and deep lakes that stratifies. And the upper column here shows then the TN/TP ratio. And the lower one here is the inorganic concentrations of nitrogen. So that would be mainly nitrate and ammonia. And on the x-axis, you have the season from winter to summer to winter. So if you take the upper one here, looking at the shallow lakes, you can see that during the wintertime and springtime, this TN/TP ratio is very high. So that indicates that it's not limited by nitrogen because there's plenty of nitrogen in the system. And if you look for the inorganic forms, there's a lot of nitrogen also. That may, of course, differs a lot between countries, but in Denmark, we have a lot of agriculture, so there's a lot of big loss of nitrogen from the agricultural fields, especially during wintertime and springtime. But you can see also that during summertime, this ratio becomes very low, and the inorganic concentrations of nitrogen also becomes very low. So there's a shift during the season, which this is a limit where you say it becomes limiting with nitrogen instead of phosphorus. So there's higher likelihood that nitrogen becomes more limiting during summer, because during summer you have this denitrification with loose nitrogen. You have maybe internal loading of phosphorus from a sediment, which also adds to the lake. So there's a higher chance that nitrogen becomes more limiting during summertime. So it's not just 1 Newton, it may be more newtons that actually are setting the conditions in the lakes. So we should not forget nitrogen when we try to manage our lakes. It can also be very important, and maybe also some difference between temperate zones, as in Denmark, or more subtropical or even tropical areas, more south. So it may also depend on your region, which one is the most important. Then I'll talk a little bit about this nitrogen and phosphorus cycling, mainly focus on phosphorus. This shows actually a sediment from a Chinese lake in Lake Taihu, where they took some sediments, and you can see when there's light, then they grow, the phytobenthos grow on the surface, and that also impacts the cycling of newtons between the sediments and the water column. If you look at how the lakes actually response, if you try to compare input-output and then look at the losses, then you have phosphorus. It can be lost by sedimentation. If the phosphorus is built into phytoplankton, then it's sediment and goes into sediment. It can also be bound into different inorganic forms like iron and aluminum and calcium and clay and other different things. So it can be both its organic form and inorganic form, which then may go down to sediment, and where it may be eventually become immobilized permanently. But it can also participate in some of things happening still in the lake water, and I'll come back to that, this internal loading of newtons. If you look of nitrogen, there you also have input and incorporation of nitrogen in the organic matter, which may sediment down and go to the sediment. But another important factor here is that you also have denitrification. So that means if you have some nitrate in the system and some organic matter, which can be decomposed by denitrifiers, then you can also lose nitrogen by denitrification. And that's usually quite important factor for the loss of nitrogen when it comes from the input to the output of the lake. So that's an important component. Another point I would like to make here is there's also a difference between deep and shallow lakes. In the deep one, you have this stratification due to this difference in the temperature. So that means that during summertime, there's almost no change between interchange between the surface and the bottom water, between the epilimnion and the hyperlimnion. Compared to if you have a shallow lake, there's a complete mixture all the time. So that means any release from the sediment will go right away to the water column, where it can be taken up by the phytoplankton. And that's not the case in the deep lakes, where you may stay in the deep parts of the lake and do not go so easily into the phytoplankton primary production. So there's a difference in way the deep and the shallow lakes function in relation to the cycling of nutrients. This is also shown in this one. It's also complicated, but I'll explain it. Again, we have on the x-axis here from winter to summer to winter. So there's a whole season here on the x-axis. In this case, we also have shallow lakes and we have deep lakes. And there's 3 types of lakes. These are the most Newton poor ones, with total P below 0.05 milligram per liter. And these are the most eutrophic ones. So there's a gradient in phosphorus coming from here to here. And what is shown in these box plots is actually the total phosphorus concentration. You can see up here when you have noticed Newton per 1, of course the level is lower, but there's not a big difference between winter and summer. There's a lot of variability, but there's no real difference between winter and summer. But if you go into the more eutrophic ones, you have this seasonality where you see a much higher concentrations during summertime because you have an internal loading of phosphorus from the sediments, and that's very depending on the temperature. These are, I should say, these are concentrations in the epilimnion, in the surface of the water column. If you then try to see what happens in the deep lakes, it's actually the opposite. During summertime, all types of lakes, the Newton poor and Newton rich, lose phosphorus from the surface. And that's because during summertime, when you have this stratification, phytoplankton taking up phosphorus in the surface sediments and take phosphorus away from the epilimnion. And then it goes to the sediments or the hyperlimnion of the lake. So there's a difference in the way that the lakes behave regarding the phosphorus in the surface of the lakes, depending on deep and shallow lakes. And I should maybe say that Danish lakes are relatively rich in Newtons, so it may be a bit different depending on which country you are from and how eutrophic they are. But there's a big difference between these different types of lakes. I would also like to mention here that we also sometimes have temporary stratification. It's not just mixed or completely stratified. There are something in between. If, for example, try to take the temperature in August, that's late summer in Denmark, and you try to see this on the gradient here in the depth gradient, and you try to see the difference between the temperature in the surface minus the temperature in the bottom. This is what you would expect if it's a completely mixed lake. There's no difference. It may be warm in the surface, but it's also warm at the bottom. If you go to the other way, you have a completely stratified lakes, warm temperature in the surface and cold in the bottom. But if you go out and measure, you often see something like this also. You still have warm in surface, and in the deep parts, it may be a little bit between what you expect from totally stratified and totally mixed. And that indicates that something happens when these lakes during the summertime, because if there was the other 2 times, you will see another temperature gradient. So in this case, you see a big difference between this surface and bottom temperature compared to this one where there's hardly any. If you then try to use this, in this case for a number of Danish lakes, and compare this difference between surface and bottom to the maximum depth, you see that if the maximum depth is low, there's no difference, because then you have a mixing of the water column all the time. If the lakes become deeper, then there's a big difference between the surface and the bottom. So this Ts minus B is high. So this indicates the difference, but you also find a lot of lakes here in between the maximum depth of 5 and 10 meters, though they have not very low but not very high levels either. It's a little bit like the green one over here. So there's some in between. And if you try to look what happens, this just shows a depth of very small and it's not that deep lake, but still you have temperature gradient, not that big, but you give anoxic conditions in the water in the deep part. And during this, you have much higher concentrations of phosphate because you see a release of phosphorus from the sediments, which goes up in the hyperlinear because during this period, it's stratified. But if it destratifies maybe later, then all this phosphorus being accumulated here in the bottom will go up to the surface and then can go into the phytoplankton and give rise to primary production. So you could say that the worst of these three types are actually this lake type with temporary stratifications, because it's sometimes build up high concentrations, which are then being mixed completely with the surface, and then you can give rise to much higher concentrations of phosphorus in the water column. Another point is also that because you have this temporary stratification, when you mix, every time you mix, the new bottom water will have a higher temperature. If you have this typical dimity one, it will stay cold for the whole summer. But this one will be higher and higher every time you mix the water column. Then it starts from over again. So maybe, as you can see, in this case, it's not really cold. It's 12 degrees. It should have been 7 or 8 compared to the Danish levels. So there's a big difference. And we also try to use this in this one that shows then, if you try to see the difference in this ratio surface to bottom, this is TS minus B is 2, so that's a very small difference, and this is very high. So this is where you would expect them not to stratify during summertime, because the difference is low. And this shows then on the scale on the maximum depth, because the deeper they are, the more you expect them to be stratified. And the y-axis is the area. And the smaller lakes are, the more easily they become stratified because they're not so easily mixed. But if you have some big lakes, they will mix to a deeper part. This is almost based on these 436 Danish lake in Denmark. And it shows that here you have this stratification, but in this range, you can have these temporary stratifications. And if you try to look at a typical lake, maybe maximum depth of 10 meters, then all the lakes from less than 1 hectare up to more than several hundred hectares can stratify temporarily. Of course, these temporary stratifications depends very much on your climate. If you have a high storm or a lot of wind, or they're protected or not protected from wind, that will impact also how easily they stratify during summertime. This is just to illustrate that this lake type with temporary stratification is quite common in Denmark, and I guess in most parts of the world also, where you have these not that deep lakes. A simple way to actually see this, if you want to know this, would be to go out late in the summer before you have the turn out and mixing in the autumn, to see the difference between the surface and the bottom. If that one is small or not in 16, there's a complete mixing. And if it's very high, then there's a complete stratification during the summertime. But if it's somewhere between maybe 2, 5, 8 degrees, depending on your climate zone, then you would expect it to stratify temporarily. And that would be a very easy way for you to know if that's actually the case. Okay, then a little bit about the nitrogen dynamics. It's a very simple one here. You have some input, you have some primary production, you may have some sedimentation, you may also lose nutrients to the outlet, and you may also lose through denitrification. If you try to look how important nitrogen are, they of course are nutrients for the phytoplankton, where they are built in the organic matter. But another point is also to remember that it's actually our carrier of oxidizing, reducing capacity, because it can change its valence, so it can change from being very oxidized in the nitrate form or very reduced in the organic or this ammonium form. So that's important for the whole metabolism in lakes. This transfer or the capacity of nitrogen to be oxidized or reduced to transfer energy between the different components in the lake. And we may also remember that nitrous oxide is a greenhouse gas, which is very important in these days about the climate changes. A little bit more complex, but basically the same. You have some production. You can have a fixation of from cyanobacteria, for example. Or you can have some simulation of the, oh, sorry, something happened here. Yeah. Or you can have this sedimentation. It goes into the sediment, it becomes mineralized, and you can have ammonia, which can be oxidized if you have some oxygen, which may go into nitrate, which may be denitrified, and they go to the lake water and eventually lost to the atmosphere. And then you, of course, also have some input from outside. So that's very, very general and typical scheme of nitrogen. If you take the same one for the phosphorus, you get phosphorus from different rocks. Nitrate mainly, or can come from fertilizers being spread out on the fields, but phosphorus come from different sources in the catchment, where by weathering and rain and rivers are led to the lakes. If you try to make a little bit the same scheme as before, you have some inlet, you have some incorporation in organic matter, you have some sedimentation, you may have some resuspension. And when it comes into the sediments, you can have many different forms of phosphorus. It may be bound in organic parts, but it can also be bound in a number of different inorganic forms, and where iron is very important in taking up the phosphorus. So if you try to look at the difference between N and P there, you can say that phosphorus cannot be fixated as nitrogen can. So it comes from inlets or maybe from internal sources. And phosphorus do not disappear by denitrification because it cannot be lost. So one phosphorus is in the system, it stays in the system. It may be permanently immobilized in a sediment, but it stays, it cannot leave the same ways as nitrogen can. And another difference is that phosphorus accumulates in a number of inorganic forms, whereas nitrogen is mainly in organic forms in the sediment. I'll just show one example here just to illustrate how important the phosphorus may be in relation to this internal loading of phosphorus. This is just Lake X, a typical lake, a small lake, relatively shallow, short retention time with some newtons, and then some typical values for total P in the sediment. You don't need to look into this. It's just to set the scheme for this one. Because if you then take this Lake X, and then you say there's 1 P in the water column, this is 1 meter deep, and you look at the upper parts, 15 centimeters of the sediment, then there will be 3 P's entering the lake each year, and there'll also be 3 P leaving if it's in equilibrium, more or less. But if you then look into the sediment, there'll be 1,000 P's in the sediment because it's much, much more concentrated compared to what you find in the water column. So there's 1,000 P's here. So in this example, Lake TP in relation to the loading from outside the sediment is 1 to 3 to 1,000. So therefore it's clear that any mechanism which impact this interchange of phosphorus between the sediments and the water can be very important for what you see in the lake water. This is just to show that what is in the sediment is very high compared to what you usually find in lake water and also what you find entering the lake. So we can also ask, is sediment a sink or source of phosphorus to the surface of water? And it depends probably from the country. Because right now in Denmark, we had experienced a period for 100 years ago where we had a low loading. In this case, there's more phosphorus entering the lake than leaving the lake. So in this case, the lake acts as a sink. It takes up some of the phosphorus. Then because we have more people, more cities and more farming, then you have increased loading from the catchment, from the outside the lake, and then increased sedimentation and very high build-up of phosphorus in sediment. Then we managed to reduce the external loading to the lake because we would like to have better quality in lakes. And then you see for a certain time or period, then the inlet is lower than the outlet, because now the sediment becomes a source of phosphorus. So that means that the change you see in the lake water is not that high because it's now the source is mainly coming from the sediment. And I'll try to show some examples on this here also. So this happens right now in Denmark. It's been happening for the past 30, 40 years because we reduced the phosphorus loading into many of our lakes from the wastewater plants in the cities back in the 70s and 80s and 90s. It may be different in your continent depending on how much you actually reduce the loading to your lakes. So it depends where you are in this time scale here. But there's three. Once this phosphorus is in the sediment, there's three factors which is needed to have this internal loading of phosphorus. First, you need to have some phosphorus that is mobile, that actually can be released. So that can be some kind of inorganic forms or in organic forms, which actually can be mobilized. So the next part is that you also need something that mobilizes it. It can be the redox potential with that. If that becomes low because of low oxygen, then the phosphorus sorbed to iron compounds may be then released, and you have this internal loading of phosphorus coming from the sediment. It can also be biologically mediated by the decomposition of organic matter. So you have some mobile phosphorus, you have a mobilization, and then you also need some transport. You need transport from the sediment to the water column above. That can be from simple diffusion because the concentrations of phosphate in the pore water is high compared to the lake water. So therefore there will be a diffusion upwards from the sediment. It can also be due to gas ebullition, bubbles of gas formed in sediment which raise to the lake water above, and then also bring some of the nutrients in the sediment up to the water column. And there can be other forms like bioturbation from benthic invertebrates or fish or birds. And you can also have wind resuspension, which brings up the sediment. Number of different transport mechanisms. But if all these three, you have a lot of mobile phosphorus, you have a high mobilization, and you have some high transport mechanisms, then you have a risk of this high internal loading of phosphorus coming to the water from the sediment. And I'll just show one example here. This is from Lake Søndergaard, where we've been studying for a long time now. It's a quite small lake, very shallow, but it has a relatively fast exchange of water. So the retention time is only a few weeks. So that means it's been flushed very often by new water coming from outside. We've been studying it for a long time, since the 80s actually. And in the 80s, it still had a very high loading of phosphorus. This is a total phosphorus loading, and this is the retention from 78 until 2004. And this shows you had a very high loading, and at that time you also have a retention of phosphorus in the sediment. Then you reduce the loading because we improved the wastewater treatment to this lake, and therefore it was decreased by 80 to 90%. Loading was much lower. But now, instead of having a positive retention, the lake now starts to have a negative retention. So that means you're in this situation where more phosphorus comes out on the lake than comes into the lake. So now this lake becomes a source of phosphorus instead of a sink of phosphorus. In this case, you can see it took place for a long time. And more than, in this case, more than 30 years. That is not always the case. It depends on how large the loading has been and how fast it's been flushed by new waters. But we usually say it often takes 5 to 10 years before you are rid of this phosphorus being accumulated in the sediment after you reduce the external loading of nutrients. So that may delay the recovery of the lake that you would like to have seen. You can also see this is the same lake as before. So this is just shortly after the loading was reduced. You can see here it's this period here in the early 80s. And then you can see the seasonal thing again in phosphorus in the lake water. Very high concentrations during summertime, lower in the wintertime because then there's a retention of phosphorus in the lake. And this shows the different years after the loading reduction. Sorry, no, it's too fast. 1 to 7 years, 8 to 14, 15, 21, 22, 28, and all more than 30 years. And you can see this internal loading becomes less and less. It becomes less high during summertime compared to what it was before. And nowadays, it's much less during summertime. So that means this internal loading eventually will become less dominating. If you go to look into sediment, there's some not completely new ones here, but this shows the profile of phosphorus in the sediments back in time, just shortly after the external loading was reduced. You see very high accumulation of phosphorus in 10 to 15 centimeters depth of a sediment, whereas 15 years, 13 years later, most of a big part of this was actually being removed, and that's because it was released to the water above. So there's been a decrease in the phosphorus, but there's still some phosphorus at this time in the sediment, which then can make this internal loading happen for a long time. So this is an example where you can actually see the changes in sediment, and you can see it also in lake water after you reduce the external loading of phosphorus. And finally, I would just like to say that we talked a lot about that if you change the nutrient availability, you will also have a change biological structure. That was the first slide I showed. You see a change in fish and phytoplankton and the macrophytes. But what is also important is that when you change the biological structure, for example, if you do something about the fish manipulation, take away the fish and change the food web, then that also changed the nutrient availability. And there's one example I would like to show here from another lake in Denmark, Lake Ecoscience, which was biomanipulated in the 90s. I had taken away some of the roach. The roach are those eating the zooplankton. And by doing this, the thickets in the lake increased from less than 1 meter to more than 2 meters. But there was no change in the external loading. So the only thing that happened in this lake was that you took away some of the fish and therefore improved the thickness of the lake. It becomes less turbid. And we looked then at what was actually happening in the lake water. Again, we see a seasonal thing here from January to December, from winter to summer to winter. And if we take this one, this shows then the thickness over here, and the chlorophyll and the total phosphorus in the lake in this season. And this shows before very low thickness, afterwards much higher. And that's you see also in the chlorophyll, much lower chlorophyll after this biomanipulation, taking away the fish. And what you then see is that also the nutrient concentration change. It was very high. You see this typical internal loading during summertime, which is much less after the more clear water. And this is probably because now the sediment is acting another way, probably because when you have more light, the water is less turbid, then you have light to the sediment also, and by this you can also have some benthic production which take up the phosphorus or also oxygenate the surface of the sediment, thereby preventing release of phosphorus from the water, from the sediment to the water. And you can see this is show the retention of phosphorus over the season. You can see before there was a negative retention release for most of the summer from May to September, but afterwards it was only a short period, more and less concentration also. So by changing the biological structure, you also change the internal loading of phosphorus, the cycling of nutrients. So it goes both ways, and that's also why it's sometimes complicated to see what is first. The thing you see in lake, is that because you have a change in the biological structure, or is something else changed in your system? Okay, I think we are coming to the conclusions now to have some time for questions also. So I think that it's obvious for most people that these nutrients, phosphorus and sometimes nitrogen, is very important for the quality of the lakes. And both nitrogen and phosphorus cycling is very dynamic and influenced by a number of different factors inside the lake, not only from outside, but also what is happening inside the lake. And then finally, you can expect that this internal phosphorus loading, if you have a high loading from outside, may delay this lake recovery for many years. Okay, I think that was what I had So now it's time for questions. Should I stop sharing now, I guess, unless I need to show something later.
Thank you, Martin. This was a very awesome presentation. Thank you so much for your time. I don't I don't know if someone wrote a question in the chat.
No.
Okay, here comes the first one. Valeria says, thanks for the presentation. What is the role of silica for diatoms?
Yeah, I didn't have time to come into silica because silica is used for the diatoms to build up the frustules and the cells. And sometimes you can see that silica becomes a limiting nutrient, especially during springtime, because these diatoms, they're good starters, so they come early in the springtime. So sometimes, and in some lakes, you can see that silica becomes a limiting nutrient. It's not phosphorus or nitrogen, but can be silica. So and I think that's quite variable between different lakes if silica becomes limiting during during springtime. But that can be seen in some lakes. So there's a role also for silica. And then usually late in summer, there will be more silica present in lake water because you have a release when it decomposes organic matter and the silica in the sediment. So yes, silica can also be important.
Is there any other question? I have a question, meanwhile. Yeah. Because you have a long story in restoration of lakes in Denmark. Yeah. Because Denmark is a country where agriculture is very developed. So I wonder if, you try different strategies. So what are the best strategies? And that is one of the questions to the restoration of lakes. Yeah. But also, if you find that there are different strategies depending on different lake types. So in general, if you have to give an advice or rule out what could be the possibilities.
Yeah, as I said in the beginning, Denmark is highly populated and also very agricultural area in Denmark. So therefore, most of our lakes are quite eutrophic because you have a high loading from outside. So when we manage our lakes, the first thing we ask the managers to do is try to reduce the nutrient loading from outside, and that's especially phosphorus. And if you've done that, then you usually also have some improvement. But if it doesn't improve within a short time, for example, if you have a fish structure dominated by these bream and roads, or if you have this high internal loading of phosphorus, you may have to restore the lakes. And we have been using different types. One of them is to try to take away the fish, as we showed you example from here also. By doing this, you can create at least clear water for some time. And if the water becomes clear for a long enough time for the macrophytes, the submerged macrophytes to establish, then you can have a more stable situation, which are then more the clear water state compared to the turbid state with the phytoplankton. We also have other things. There are some issues where you try to also impact the phosphorus in the lake by using aluminum or maybe this phosphorus, which has been used at least in one lake in Denmark. So that's another way. And a final way and method which I would like to mention is also that we can take up the sediment, and that's quite expensive. But we have a project right now where we try to, at the same time as taking up the sediment, we have some people working on try to reuse the phosphorus, because phosphorus, as you may know, is a limiting source, and we ran out of phosphorus in not that far future. We depend on a few mines in the world, and once we used all the phosphorus in these mines, we need to recycle phosphorus. And the best way would, of course, instead of trying to fixate phosphorus in sediment, it would be better if you can try to reuse it in the agricultural areas or something else. Right now, that is not economically feasible because it's much cheaper to buy some new phosphorus from somewhere else instead of try to recycle it. But in the future, I think we need to focus more on this phosphorus limitation because we will run out of phosphorus. It's still here, of course, but it's very very tightly to particles in the agricultural areas or in the sediment, are very diluted when it comes to the ocean, and you cannot really find it again. Nitrogen we can fixate artificially from the atmosphere by this Haber-Bosch process, but phosphorus we cannot make it. So therefore we depend on having methods try to recycle it in the future.
Okay, thank you. Erika asked, thank you so much for your sharing. Could you suggest any management strategies for the recovery of highly eutrophic lakes? Thank you.
If I didn't hear the first one, do we have some?
Could you suggest any management strategies to the recovery of highly eutrophic lakes?
Yeah, it's more or less what I said before. The strategy is to remove the loading of phosphorus or maybe also nitrogen from outside. The first thing you should do would be to try to decrease the external loading of phosphorus to the system. And I know that's sometimes not so easy, but that's, if we want improvements, you need to do something from the loading from outside. You could do something inside the lake, but it will not last long because then it'll return back again to the turbid state if you still have a high loading from outside.
Olga asks, can the internal nitrogen loading be as important as internal phosphorus loading in terms of phytoplankton impact in lakes?
So the internal loading of nitrogen?
Yeah,
I think it may be a short term, maybe at least, but it's a little bit different from phosphorus because nitrogen is only bound in organic forms, it's denatrified, so therefore it's more easily lost from systems. So it doesn't have this legacy of nitrogen as phosphorus has. So I think we see that nitrogen is more easily to manipulate because if it's depending on nitrogen, you can reduce the loading and you see the effects immediately in the lake also, if it's limited by nitrogen. So I would not expect any legacy of nitrogen or only short time compared to phosphorus.
Slawomir says, thank you for the great presentation. I have two questions. The first one is, what is the role of submerged macrophytes in pea loading?
Yeah, the role, usually see as one of the first slides I showed was that if the loading is high and the water becomes too turbid, then the macrophytes disappear or becomes very low in abundance. If you then are able to make the water more clear, then there will be sometimes some delay in the recovery of macrophytes because they may be lost from the lake or the whole watercourse, so it may take some time to recover. And sometimes the sediment may also be in the bad conditions for allowing the macrophytes to grow. But it's important that you have the submerged macrophytes back, especially in the shallow lakes, of course, because we can see, and it's been shown many places, that the macrophytes have a good stabilizing factor for having more stable clear water conditions. So one of the success criteria for restoring shallow lakes is often or usually to have the submerged macrophytes back. And I know there's been some problems somewhere if they cannot grow there. We all seen sometimes that the water birds actually prevent them from coming back because they've been eaten by the water birds. But usually when you establish clear water conditions, then the macrophytes are able to take over quite fast. It depends on which species, but some species can go from almost nothing to almost 100% cover within 1 or 2 years.
Yeah. The second question, you already answered it because what is your opinion about sediment removal as a restoration method? So you already asked that.
Yeah, well, I may add that it's also very costly. It's very expensive to take up the sediment, and sometimes you also may have some problems getting rid of the sediment, because if it's been polluted by wastewater from a city or a factory, then you may have something in sediments, heavy metals or pesticides, which you will not like to bring out in the agricultural areas and then bring into the food chain and in the humans. So there may be some problems with taking up the sediment. Also not only the process itself, but also what to do with the sediment afterwards.
Yes, and also it would be no option for a paleolimnological analysis in those type of lakes if you remove the sediment.
Yeah. Yeah.
Okay. Oren says, thank you very much for the presentation. Can you elaborate on how changing redox potential can mobilize phosphorus from the sediment?
Yeah, so the main thing is that phosphorus is, when it's with oxygen, then iron is in an oxidized form, iron 3. And this is a form that is able to absorb or take up phosphorus and have a high capacity to absorb phosphorus. But if redox becomes too low, and that becomes low if there's no oxygen in the system, if it becomes below approximately 200 millivolts, then oxidized iron will become reduced. And when iron becomes reduced, it becomes also dissolved. And therefore it cannot take up the phosphorus anymore. So what you will typically see is that if oxygen becomes low, then the sediment loses its capacity to take up phosphorus, and you see this release of phosphorus from the sediment. The sediment can also be oxidized by nitrate. If you have high concentrations of nitrate, then it will still prevent release of phosphorus, because nitrate prevents low redox potential also. But usually it's a matter of oxygen and the capacity of iron to retain the phosphorus.
Thank you. Daniel says, great presentation. I am curious as to how effective nutrient load reductions are in shallow lakes with long water resistant times.
Yeah.
If quickly flushed shallow lakes take more than 5-10 years to recover, what is the time frame for recovery in lakes with water resident times longer than 1-5-10 years?
Yeah, that's also a problem, yes, because if the residence time is very long, of course, the phosphorus already in the lake cannot be flushed. So we have some lakes in Denmark where the retention time is more than 10 years. In that case, it will of course take even longer time, because now it's not only the sediment, but also the phosphorus already present in the lake that needs to be flushed out before you see any changes. So therefore, it's not only sediment, but also the retention time. And we have some lakes, and maybe especially lakes which are more or less isolated in the landscape, which have become eutrophic maybe in the past time because of some loading from outside. And they are very difficult to become limited by phosphorus, because you have phosphorus in the water and maybe also in the sediment. And if there's no flushing going on, it can stay there almost forever. Eventually may be buried deep in the sediment because you have new sedimentation all the time, but it takes a long time. So it is a problem if you have lakes with a very slow flushing of new water coming from outside. In that case, you may need to restore them by some kind of thing that can fixate the phosphorus in the water or take up the sediment.
Lone asks, excellent and informative talk. Please explain how diatom proxy is important in mangrove ecosystems for environmental dynamics.
Oh, I don't know much among mangroves, so I don't think I dare to talk about that, because mangrove is a system I never worked in, so I don't know how it functions regarding the silica. So I would say no, I can't answer that. Okay. Maybe someone else can. I don't know much about mangroves.
Okay, the next one is Paula that says, thank you very much for the seminar. How does horizontal mixing affect the cycles of nutrients in lakes?
How does what?
Horizontal mixing.
Oh, horizontal mixing. Okay, yes. Yeah. The lakes we have in Denmark are mostly relatively small, so this horizontal is not that important, I guess. But in larger lakes, there's of course some mixing, and it may create some internal water movement, which also mix the water column. But it's mainly what we see in Denmark is it mainly that the mixing mainly depends on the wind creating some turbulence in the surface, and of course the more protected the lake are, for example if it's a small lake, then the stratification may start only a few meters below the surface of the water. But in large lakes it can be important you have some wind which mix deep, and some lakes may then be mixed down to 15 or 20 meters maybe, because you have this impact from the winds on the circulation of water. And that may this horizontal thing may also, in these cycles in the lake, may also impact in how it can mix in different parts of the lake. But I have not much experience in this from the Danish lakes.
Okay. Jasper says, thanks for your presentation. I have a question regarding phosphorus nitrogen limitation. How were the Durst holes NP22 and NP9 determined? Yeah, that's determined in a way that the phytoplankton needs these nutrients to build into organic matter. And they need more nitrogen than phosphorus because it's used in amino acids and other things. So therefore, that's the level that is needed in the organic tissue of these different species. It depends a little bit where you set the limit, but usually say by weight it's these about 20 and 10. So it's a matter of how much is needed for the phytoplankton to incorporate in when they build up new organic matter. Okay. Adel Rahman asks, in your opinion, what is the best method to manage eutrophic lakes? Yeah, I think I said that before. That's to reduce the external loading of nutrients. You'd have to take care of what you put into the lake, and if there's too many nutrients, the phytoplankton will take over and make the water turbid. So this external loading of nutrients is the primary thing you should do. Reduce that one, if possible. The next question is by Losal. Thank you very much, Dr. Martin Søndergaard, for your very informative presentation. The largest lake average depth is 2 meters. In your country is currently hypereutrophic, and there was a plan before to dredge the lake. What will be the implication of dredging nitrogen and phosphorus in a lake? Yeah, the implication would be that if you take away, if it's a lake that is very impacted by internal loading of phosphorus, then you can reduce, maybe not completely take away, but then you can reduce this internal loading of phosphorus. And if that is successful, you would expect a much better lake after the sediment dredging, because you take away some of the nutrients that otherwise would go into the lake water and feed the phytoplankton. Okay. Caleb asks, thank you, Professor, for your presentation. Could you explain how macrophytes, floating, submerged, and emerged growth influences nitrogen and phosphorus cycling in shallow lakes, particularly in Denmark, compared to maybe hot countries? Yeah, there may be differences. It's for the macrophytes, they have different mechanisms which they can be kind of refuge for the zooplankton, so they can hide inside the macrophyte beds and therefore not eaten that easily by the fish.
They can prevent resuspension of the sediment. They can maybe oxidize the sediments. They can bring maybe oxygen down into sediment by the roots because they produce oxygen. And they can be the place for epiphytes sitting on them. And so there's a lot of benefits from the submerged macrophytes. In the tropical, I'm not that familiar to that, but I know that in the tropical you have many more fish usually. So it's probably more difficult to make the submerged macrophytes important because you have a lot of small fish also, which can also go into the macrophytes beds and maybe still eat the zooplankton that would have been there. So I think I think that it may
İyileştiniz mi?
may
Süper.
not be that easy
Geçmiş olsun canım.
to control the zooplankton by having
Ay yok,
macrophytes
6 aydan önce
in tropical.
olmayalım ya.
There's someone talking here.
Yeah, Erica, please could you? Yeah, that's okay. Thank you, Erica.
Okay. Yeah, so I think the benefits we see from the macrophytes in the Danish lakes may be less when you go into tropical areas, but you may know more about that than I do. I think you can still have some benefits, but maybe not so much compared to what we see in temperate zones because of the fish.
Yes, also there are a lot of fish that eat macrophytes in subtropical and tropical
they're
lakes.
different because of the fish in the tropical areas.
So it's always is required to remove fish to have a successful biomanipulation of the lake.
Okay, yeah.
Justine asked, thank you for the presentation. Does the origin of the lake, for example, volcanic, have an effect on the nutrient concentration of the lake, especially once it gets to the sediment?
With volcanic ashes, I don't know much about this, but I guess that volcanic ashes can be quite rich in nutrients. At least you see that people like to grow agriculture close to volcanic areas. So I guess that they could impact the lakes, but I don't know much about that. I guess it also depends on which types of volcanic it is, but I guess it would impact because it would also introduce more nutrients. But I'm uncertain on this.
Lon asked, what should be the optimum drying temperature of the sample processing for nitrogen isotope analysis? Does drying at higher of 50 degrees cause nitrogen loss from the sediment? So this,
I'm not sure I follow that. It's something about the temperature.
Yeah, it's about the temperature that is needed to process nitrogen isotope analysis. And she is asking, but this is very specific question about if drying at higher than 50 degrees cause nitrogen loss from the sediment. No, I think not, because for isotope analysis, most samples should be dry at 60 degrees. So I don't think it causes any loss, but you should check on in the bibliography better just to be sure for that loan. The next question is from Lara. Excellent presentation, thank you. I would like to ask you your opinion about adding oxygen water as a restoration technique after reducing the external phosphorus load. Peroxide of hydrogen.
Hydrogen peroxide, H2O2. Okay, yeah, I know it's been used in some countries, or at least as a potential restoration. As far as I know, it may have some short-term effects, but only short-term, because after some time this disappears and then the lake will come back to the state it had before. So in my opinion, as far as I know, it's not any permanent solution for cleaning up your lake.
Okay. Luis Mark asked, Thanks a lot for your time and your presentation. Could you elaborate about benefits of good macrophytes for stabilizing the sediments versus negative aspects of exotic invasive macrophytes, such as Myriaphyllum spicatum, regarding eutrophication?
Yeah. I think that in all cases, I think overall, even though some of these invasive species can be very dominating, I think that for the lake quality, they will probably still have some benefits because they make clear water and higher biodiversity. But of course, if invasive species takes over, it can have some negative impact on the local species because then can maybe not compete with this very fast-growing invasive species. So in that way, it's not good. So I think usually you would like to have species that are adapted to your own region and having them back instead of having some native species coming in. And in Denmark, we have the Elodea canadensis for more than 150 years. I don't think, maybe you cannot call it invasive anymore, but it's very dominating sometimes also and can completely take over within a few years actually. And I guess for Myriaphyllum it could be the same in some lakes where it's some countries where it's not usually coming. So in most cases I think they will benefit still, but it's better to have the local species come in and dominate instead of invasive species.
Okay. And Lone asks, does lake organisms... sorry, that there is another question and it moves. Okay, here again. Does lake organisms like gasteropods shell contribute to lake productivity and internal dynamics?
Yeah, like gasteropods, shells. So only the shells. So not living gasteropods.
No, the shells. She's asking for the
shells. I guess these shells will be dissolved eventually, but it's mainly calcium carbonate and maybe not very important for the lake. That's my opinion. Yeah.
Virginia asks, thank you very much for your presentation, Martin, and greetings from Uruguay. We have monomytic lake under aeration without visible effects on stratification nor hypolimnion hypoxia during summer. Could the aeration still have another effects?
So you don't have, you irrigate you aerate.
They have monomytic lakes under aeration without visible effects on stratification or hypolimnion hypoxia during summer. Could the aeration still have another effects?
Yeah, but if it's monomytic, it's not mixed during summertime at all, so it stays down there, as far as I understand. Yeah. So in that case, I guess it's not for what is going on in the surface of a lake is maybe not that important because then it's not impacted by the hypolimnion water. So we have a monomytic, I can read it now also, we have a monomytic lake under aeration. So you aerate it artificially, I guess. Virginia, yeah.
It seems so.
Yeah. I think that the aeration may have effects on. Okay, hi.
Yeah, hi.
I see. So it may have effects on the hypolimnion.
Restoration measure that the neighbors of the lake are implementing, and we aren't seeing any the typical effects that you expect from the measure. Right?
So do they actually mix the water?
Well, that's the thing that we still see the stratification during summer, so the aerator doesn't seem to have the energy enough to destratify.
No. So would you like to destratify the lake?
Well, I'm wondering if there could be another effect that goes in the line for restoring the lake. without the stratifying.
Yeah, I think sometimes these aeration products, we also have some of those in Denmark, but mainly in the deep parts. And our experience is that need to go on for a long time, maybe almost forever, to have some infects. And maybe that's not what you need or would like, because you would like to do something that will last without having some equipment standing there for many years. So again, here I think I don't know if you can control the external loading of newtons, because sometimes these things you do in the lake is maybe not really working so well, because you still have a lot of newtons coming from outside, and maybe also inside in the lake. So it's sometimes I can see these products as a way to say that, okay, we do something here, and then some people can say that, oh, that's fine, but maybe they may not be that efficient in the long run. Yeah. Yeah. Any more, Maria?
No, we don't have any more questions.
No, that's fine.
This was the last one.
Yeah.
You have a lot of questions.
Yeah, that's fine. It's fine. It's good to have discussion also, even though we cannot. Yeah.
So, if there is any more questions? Okay, we have another one. Fernando.
Okay. Yeah.
Thanks for the presentation. Do you think that biomanipulation can still play a role in the restoration of shallow lakes?
Yes, but again, I would stress that it should mainly be used in lakes where you already did control the loading of newtons coming from outside, because otherwise it will just last for a short time, a few years, and then it'll come back to what it used to be. So it's again important, but I think it can be a way that you push the lake to be clear for some time, and if you, for these few years where it's clear, then could have the submerged macrophytes back, then it could come into a more stable clear water conditions. So yes, but it depends on the external loading.
Okay. Well, thank you. Thank you so much, Martin, for your time, for this presentation. It was an incredible presentation with a lot of questions. So it was a pleasure to have you in this seminar series. Thanks to all of you for participating in the seminar and asking questions. And once more, remember that the next SEAL Congress will be held in Brazil, in Foz do Iguaçu, next May. You can visit our homepage and see the detail for the registration, and also for abstract submission that will end the 22nd of December. So thank you all, and goodbye. Hope you see you, all of you, again in a short time, because we are going to have another seminar soon on December about greenhouse gases in lakes by Thomas Davison. So see you in the short future, and thank you all for attending this seminar. Thank you, Martin, once more time.
Nice to see you. Yeah.